So good afternoon, everyone, and welcome to this first 2025 event of the 40 Under 40 lecture series on combustion. It is my great pleasure to introduce the speaker of today. Is the Professor Ivan Langella from TU Delft. Ivan is assistant professor in sustainable aircraft propulsion at the Faculty of Aerospace Engineering at TU Delft. He got his master's degree in aerospace engineering from the University Federico II of Naples in 2011, and then a PhD in mechanical engineering from the University of Cambridge in 2016. After that, he has worked as a postdoctoral associate at the University of Cambridge and also as a lecturer in thermofluids and engineering in the UK before joining the group in Delft. Now is a member of several associations, including the Combustion Institute, the American Society of Mechanical Engineering, and the Dutch Association for Flame Research, and a fellow of the Higher Education Academy. Today, Ivan will talk about hydrogen flames under intensive strain. This is in the framework of an ERC starting grant that he obtained recently and started in 2023. Ivan, thank you very much for having accepted our invitation, and I give you the floor for your lecture.
Okay, thank you for actually inviting me. And can everybody, can you hear me clearly? And
very well.
The presentation going okay. As I was saying, thank you for inviting me. Indeed, I would like to, I'm going to present some of the results and investigations that we are conducting within mainly this ERC project that started a year and a half ago. And and discuss about that. So I just give a very general overview, since you, I guess, all the audience is familiar. But I mean, why we in general are interested in having an alternative fuel, and in general in hydrogen combustion. In general, we know that the world population is increasing, as you see on the left, at a fast rate, and the split of energy that we have still relies a lot on combustion for a number of reasons, partly because we have relied on that so far, and we are about 87%, but also because of some sectors that require a lot of power, and hydrogen allows you to have on demand that power. The energy, from the energy point of view, is worldwide. The need of energy is increasing a lot. The energy sector will require further and further investments in the future. From a point of view of the fuel we use, we have enough reserves for kerosene, but of course the problem is a problem of environment. So we're trying to change fuel because we want to reduce the emissions. And as you see, the energy only from 73 to 2012, so more than 10 years ago, is becoming almost 4 times higher, the requirement for energy. So we have to meet this demand, and we have to take into account that demand is increasing. Looking just at the aviation sector, since at TU Delft we are interested in the aviation, the aerospace. The number of flights is expected to increase in the years. There was a stop due to COVID, but is increasing mainly due to the middle class in the Asia Pacific regions. And so while we have to reduce the emissions and try to have better, cleaner skies, we have to take into account this very fast-pacing demand, which is increasing over the years. Okay, so this is the rationale. Now we go to hydrogen flames, and the interest of hydrogen is because we don't have carbon, as we know. So in this graph that we see, other than not having CO2, of course, if you potentially burn hydrogen 100%, you will also not have CO. And if you see, I'll put a point You can reduce NOx in principle just going towards lower temperature that you in principle could achieve by going to linear conditions. However, hydrogen is a bit tricky for a number of reasons. First, if you assume the graph on the left, bottom left, as you decrease the equivalence ratio, it's true that NOx decreases because of the thermal NOx route, but the NNH route becomes more dominant, so the decrease is not as strong as you would expect. If you add to the fact that you have instabilities that can occur, which you didn't have for other fuels, like thermodiffusive instabilities, then of course it means that we need to reinvent, or at least redefine how we build the combustion chambers. And in this graph is the general graph, is not for hydrogen, but general graph that shows that indeed changing the fuel-air ratio and the air mass flow, then you can incur either high frequency oscillations or flashback, and the boundaries where you have this in the case of hydrogen are different, significantly different than from other fuels. And in general, the challenges are already present if you go linear condition with any fuel. This is videos taken at the laboratory in Delft, so credit is for the experimentalists that I put it here. If you see now, this is just a runoff, and I took the video, so that's why it's not as good as it could be. But if you go to linear condition and if you don't put enough care in how we design it, we can have situations like this with very strong instabilities. And unfortunately, with hydrogen, these conditions at which these instabilities occur are different and not easily predictable. So what are the challenges indeed? So, and I go brief because you are all aware, but mainly, and I'm gonna discuss mainly about premixed conditions, which are the one of interest for this talk. So you can have, because of the strong differential diffusion effects in hydrogen, you can have a variation of mixture fraction along the flame, because hydrogen moves ahead of oxygen towards the products, and thermodiffusion instabilities, for which the overall consumption speed increases because the wrinkling increases. And the additional challenges in case you have problems with autoignition or you're close to autoignition because of the very low autoignition delay time of hydrogen. We are generally around the third limit of explosion that you see here, because the general combustors we are considering gas turbines are obviously above 1 bar. And this causes additional things that we have to take into consideration. First, the flashback may become more a problem due to autoignition. If you are close to the temperatures that lead indeed to the to be in the explosion part of the diagram. And to give you an example, this is a work that was run by a number of students in Delft, and two of which are now PhD students, which are Minea Flores and Pablo Rocco Pausada. And this is a simplified combustor, which is taken from a geometry from Ansaldo of their heat combustor. It's a simplified. This is to show the difference of what happens at what atmosphere, for example, where the flame is already unsteady, quite unsteady, but doesn't flash back to 20 atmosphere, where because of autoignition, the flame suddenly flash back, as you see. Now, the recent work actually that has been published in the Proceedings of Combustion Institute show that we can predict that, and this is work done by Minea Flores and Anko Adoan in collaboration with Richard White as well, and of TU Delft. As you see, using some machine learning, which I'm not an expert in, that was from the collaborators in IS Bangalore from Ancoa. You can, using water injection, basically you predict the flashback before it occurs. And as you see, water is being sprayed before even something happens, and because we got a precursor that tells us when this is what's going to happen. But anyways, this was a bit of deviation of this talk. This is to say, we have to keep into account also the fact that we may have autoignition problems when we design combustion chamber for hydrogen. The other thing is about thermoacoustic instabilities. That's because it's not that the physics is different than other fuels, but the flame response hydrogen due to its very different reactivity as compared to other fuels is different, and that could be seen, for example, in this work from the French group, where they had an injection of methane and they add little percentages of hydrogen. They see that the flame response, where the big circles indicate more and more unstable conditions to thermoacoustics, shift and changes completely even with the small injection of hydrogen. So that tells us that we need to reevaluate also that part to understand to understand how to build a safe combustion chamber when we use hydrogen. And of course, all these problems are becoming worse to the fact that having experimental data at relevant condition is very, very challenging, especially for the unstable conditions, of course. Okay, with that said, I'm gonna now give some recap a bit of the physics of the strained hydrogen flames, of what we in particular are finding out in our research. Mainly, the idea is this: if you strain an hydrogen flame, the flame becomes stronger due to the fact that due to the differential diffusion at least up to a very high applied strain level. And the main thing, which was already published and observed in this paper that is reported here by the PhD student that worked on it, Alessandro Porcarelli, and is that NOx overall goes down. I'm gonna give you a bit of the hints of the reasons. Of course, there is also the paper, but that's the main observation that we have. And then the project, otherwise called DCRC, based on this, try now to exploit this principle in combustion chambers and see how we can control the level of strain to achieve lower NOx. And that is done not only by strain, but also by water injection in the project. So I just give a quick introduction of the team. The team that is working on this is composed by 4 PhD students and 1 postdoc that are shown here. There is a PhD student in visit from University of Cairo that is currently also working on this. In support, even if not directly working on this, there is a lot of interaction from other projects that benefit this ERC, with other 4 PhD students working on other aspects, but which intersects at certain points with also the high strain. And I want also to acknowledge actually the experiment, my colleagues, and the team of PhD students, which I didn't show the faces, otherwise that would have been too messy, but that also in parallel are working on the side of the experiments for this research. All right, so let's try to understand what we're talking about. So, if we have a lean, starting from a lean, flat, steady flame, what is the effect of differential diffusion? That, in that case, is only to leaning, so reducing the local equivalence ratio, as you see from the graph on the right. So, a flame like this, you only have a reduction of mixer fraction, which actually leads to a reduction reaction rate. the fact that the flame becomes stronger is when you have curvature or strain. That is when that happens. See, here is the definition of strain with the two components of stretch, with the two components of strain and curvature. The configuration that I'm going to focus most is the strain one. So where we have no curvature, but an opposite jet configuration so that we only have the strain components. That is because you can achieve level of stretch much higher than those that you can achieve with curvature only. And that's why it's more interesting, as you will see. A note, the stretch effect in general, and so the strain, becomes effective only when the flame cannot move anymore and in presence of differential diffusion effect. So things that we see we have to go to relatively high or moderate to very high strains to see them, because the flame at a certain point cannot move anymore, and that's where we start to see interesting effects. One of the very important thing is that the Marching length, which is defined basically it's a measure of the variation of the flame topology, and it's equal to the derivative of flame speed towards stretch, inverts its sign, so it becomes negative at at the link conditions, as you see from the graph on the left. The inversion point is about 0.7, 0.8 of equivalence ratio. And because of that inversion, the maximum flame temperature and the flame speed increase with the stretch. Now, this graph that you see on the right is actually a sketch, which is a bit misleading because it looks like once you reach the peak, after that you get to extinction. In reality, and then I'll come back to that later, we don't reach extinction. After that, the flame speed starts to decrease again, but the flame is still quite robust. And only after a while, you start to have the extinction. But I will be back to that. So, as I was saying, when the flame is flat and freely propagating, we only have, as you see on the left, a decrease of reaction rate. When you have stretch, then in this case strain, then you will have the overshoot also of the equivalence ratio that you see in the graph on the right. And then that is what causes, for example, the increase of adiabatic flame temperature. So you go to a super adiabatic condition, and increase of equivalence ratio. One thing to notice, and that is the research, recent research from Alessandro Porcarelli, which was published in the Combustion Institute. Actually, as you see, the effect of the strain is actually to limit the effect of differential diffusion. If you see on the left of this graph, so if you go from very low strain to very high strain, this effect of leaning is becoming lower. And that can be seen also in these other graphs. In other graphs. I'll show that in a second. Overall, the research shows, this is for laminar condition, shows that we have an overall decrease of NOx. Now, in this case, in terms of NO, but we also see that for N2O. And the reason of that for the laminar condition is that the OH radical is mainly dictated by the behavior of the OH radicals. The flame is very robust, it's very far from extinction, so it's not a problem of residence time. And the OH peak increases, as you see, so decreases, as you see, if you go to high strain. If you see, though, on the graph on the right, a bit more in detail, you have a peak increase first. And that is in the flame. And that is because this is due to the fact that of the superadiabatic temperature. So OH first increased because of the superadiabatic temperature, but then it goes down, and the reduction of NOx overall that you see on the top, the fact that NOx goes down, is mainly due to the post-flame in the laminar conditions, because what happens later, or the OH radicals that go down, and they basically become not available anymore for the reactions that involve the NOx. This, I want to specify again, is not a matter of residence time. We had checked a different, with the 2D simulations, in this case, at different positions, different plane, comparing at same time from a parcel that starts from the inlet for different strain, and the reduction of NOx that we see overall in terms of the flux through these boundaries is stronger. Well, it's still effective. So even if we compare at different positions, because you may argue, okay, as you increase the strain, you increase the velocities, and then you have less time. Even if we compare at same time, we see this reduction of NOx. In general, how we can exploit, we thought we can exploit this principle. If you see on the graph on the left, bottom right, this color diagram, you see that basically, in general, you can reduce the NOx by go to linear condition, but we know that we have differential diffusion instabilities, thermodiffusion instabilities that can arise. So instead, we can act by straining the flame more and achieve the same reduction of NOx, as you see this iso contour and iso lines of NO, without having to go too far into the lean zone. That's the main thing. So we can use strain instead of going super lean. We have now in further research, and the reference is wrong. This is research being done by Mohammed Fatih here in Delft. We are studying now the effect also of at turbulent condition, using a DNS code and different conditions here. Sorry, there was some problem with the slides. Different condition of equivalence ratio. Mainly at 0.7, you have more or less the Martian length, which is 0. At 0.5, you have a negative Martian length. That's the choice for increasing level of strain, applied strain. Now, what we see, and this is a video of the condition of the flame, which, as you see, moves as soon as it becomes turbulence towards the inlet on the left, because accelerates due to the wrinkling. More or less, we see the same thing. So the message is a turbulent condition. Also, you see the reduction of NO for the same reasons that we see on the laminar condition. Actually, it becomes better in the sense that if you see here, where the dashed line is the laminar condition and the solid line are the turbulent condition, this is only, on average, what happens on the flame. I said before, on the flame, in the laminar condition, and this is reported here, actually NO increases because the OH radical increases. In turbulent condition, however, the effect, which is a thermal effect, this thermal effect doesn't exist, or doesn't exist much, because the turbulent eddies reshuffle the flow so that you don't easily reach the superadiabatic condition, or less easy than in the laminar case. So the dominant effect becomes the reduction of NOx in this case. So this is, by the way, data that we are gonna we are submitting now. We should be submitting in the next few weeks. Okay. An additional note: this is research by PhD candidate Maria Rosaria Acquaviva. Soret effect, we all know that is important. We see that by not including it, especially a lean condition, we may predict wrongly a number of quantities. Here, the additional thing that we have studied is the effect of strain. So if you see the variation that you see between the dashed and the solid line increases with strain. So if you go to high strain regimes, the importance of the Soret becomes stronger at both lean and less lean conditions. You see that the deviations are stronger at lean conditions, as you see from this graph. And of course, then you will have quantitative difference also in the NOx with among all the important routes, as you see in the graph on the bottom. But the additional thing, which is very important, is that because of this, you have an inversion, well, not an inversion, but you have a change in the position in which the Martian length inverts. It's not a strong change, but it's a change of 10 to 20, well, around 10%. But it's still relevant because if you are in a condition in a combustor where you target, for example, an equivalency ratio of 0.7, now it's important to know if you have a flame speed that increases with stretch or decreases with stretch. So that's the main message that we wanted to that we observed. Okay. We tested also the water injection, although this part of the research is more preliminary. We did some preliminary simulations in laminar condition and 1D. The main message from this simulation is, first, even if when you have a mixture in the inlet where there is some water in form of gas, the decrease of NOx still happens with strain. Of course, NOx overall goes down because you are putting water which absorbs heat. That's the reason. But interestingly, if you see two conditions at equivalence ratio 0.7, where the Martian length is almost 0, and 0.5 when it is negative, we see that from this graph, these ISO colors become more, let's say, vertical. What that means is that because of the Martian length which is negative, it's easier once you start from a certain condition of water, as you increase the strain, to get back to the condition that you had at a stretched condition. What does it mean? That in the moment you inject water, you reduce the temperature, you can use the strain to get back that temperature, because that will tend to increase the strain. This is, of course, a laminar condition. We haven't yet observed what happens at turbulent conditions. Now you're working, the PhD Maria Rosario is working on actually simulating, fully solving a droplet. The reason here is because the droplets reaching the flame front, as you see here, may induce additional stretch. And our objective is to try to control that stretch via the droplets because of the effects that it has, the stretch has on NOx that I've discussed before. It's not easy. We are only in the preliminary stage because we are working for a number of reasons and moment only on the free propagating, and this develop hydrodynamic instability, as you see. However, simulations are going on now, and again, the understanding that we want to achieve is if these droplets can be used to alter the level of strain, the local level of strain on the flame, and with that achieve a bit more control of the NOx level. A few more information. We have recently collaborated with the group of Rome of Francesco Creta and Eduardo Lapenna, with an exchange within Cypher consortium, actually. And Alessandro Porcarelli went to Rome, and the research was about the investigation of the effect of strain on the thermodiffusion instabilities. I can summarize them in a few words. I don't want to go too much into it. That is a paper submitted to the Mediterranean Combustion Symposium. Basically, if the level of strain is relatively low, applied strain, an order of 500 per second or less, there is either the thermodiffusion stability are stronger, or there is a situation of balance where the flame doesn't remain flat. If the strain surpasses that value, that's the main finding, is that the thermodiffusion stability is suppressed. That you can see for different level of initial wavelengths that we assign in the graphs on the bottom. You have to read them from right to left according to the temporal evolution, but you see that there is a region in which the growth rate goes above zero, and you have an instability region. But after a certain time, we see that always you get out of the instability region. And that time we calculate of the order of one chemical flow time. So it's very short. So what does it say? That if we can impose high strain, that will tend always to stabilize the flame and suppress the instabilities. We are starting to do some check also on thermoacoustic instabilities, and the PhD working on it is Emre Boncu. Now it's still preliminary. What we are doing is, again, of course, thermoacoustic instabilities depend on the configuration. So the objective is to try to see what happens when we have strain. Why? Because strain changes the reaction rate differently than from other fuel, which may lead to interesting observations. So we have forced at different, of course, with different amplitude, but still in the linear regime, the flame in a counterflow configuration at an equivalence ratio relatively low, 0.4. And these are results that have been submitted also to the Mediterranean Combustion Symposium, which can be summarized as this. First, if the strain is too low, we always have thermoacoustic instabilities are stronger and dominate the physics. And moderate strain, which is implied strain between 1,000 and 2,000, those are suppressed, which you see in the graph from this circle and squares. Interesting, if we keep increasing the strain, then thermoacoustic instabilities becomes again not suppressed, and the maximum gain increases, as you see here, and moves towards high frequencies. Now we try to understand why there is at certain point, as we increase the strain, this behavior, which can explain by this graph that I was mentioning a little bit before. As we increase the strain, the behavior of the reaction rate with strain, as you know, because we are a negative Martian length initially, start to increase. So reaction rate increases with strain. However, it reaches a peak at very high strain and starts to go down again. Despite the flame is still far from extinction. That's what I want to point out. It's not going suddenly dropping as you see in this graph. And indeed, that's what happened. Since the equivalence ratio is pretty low, 0.4, then we have this inversion of the Martian length at the level of strain which was within the range that we were examining. And that level, that change of sign of the Martian length changes the phase shift, causes a phase shift in the thermoacoustic response of 180 degrees. And that's, we believe, at least at the moment, that is the reason that we had this behavior, which is quite interesting if then you go to a combustor, because it's true that the thermoacoustic response there will be different depending on the geometry, but there seems to be an intrinsic effect of strain, because the reaction rate behavior with strain will change if you are in link conditions, or may change, and that causes differences in how, of course, you will have to develop or model your combustor. So the summary of all this, I want to be very quick, is basically if you have a situation with strain, if you can impose a lot of strain on your hydrogen flame, NOx is suppressed, and this suppression in percentage becomes stronger, even stronger, at turbulent conditions. Of course, at turbulent condition, the NOx increases because the flame is wrinkled, but in percentage, if you start to apply strain, you have a stronger the reduction of NOx. Then, if the strain is high enough, we can suppress thermodiffusing instabilities. And also, the strain itself, because of the dependence of the reaction rate with strain, can alter the thermoacoustic response. That is the main summary of all this. Now, the question is how to implement this in a real gas turbine. And just to be clear, I don't have the answer yet. We are working on it. But in general, we are targeting two main architectures. One is a lean premix, and one is an RQL. Now, for the lean premix, actually, we are in a moment, I don't know. We don't know what to do. There are different prototypes which we have been proposing to try to maximize the strain level, but I'm not gonna discuss them even because we don't have any real information about it. There is a little bit of study for an RQL type combustor instead that we are conducting. We are doing that for a number of reasons, including a trapped vortex cavity in an RQL configuration. The advantage of that is because adding a cavity allows us to separate, at least in good extent, the physics that happens in the cavity to the rest. And so we can deal first with the rich region and then think later what to do for the quench and or better quick mix and lean regions. The challenge regarding using hydrogen, of course, there are different challenges because of the architecture itself, but the challenges with hydrogen is that hydrogen is so reactive that despite it's very diffusive, it doesn't have time to mix, and then you can have diffusion flames, which would produce a lot of NOx. And I'll show that in a second. So you know this graph, it's a very simple graph. As you see, you would like to avoid the non-premix region, of course, and move from the rich region to the lean region in the RQL without passing from the diffusion flame or near stoichiometric condition. So we started with the model that we took from the literature. We are investigating that at low TRL level and moment. The part that I want to mention is that to try to help the mixing, so to make sure that hydrogen mixes first before burning, and so avoid the diffusion flame, you can use strain in the exact opposite way that it was used for the lean condition. Because in this case, as you see here, the strain, unlike the lean condition, which has exact opposite effect, will reduce the time scale first, okay? So you can slow down using the strain, but we did check, unfortunately, even if we get to 1,000 of applied strain per second of applied strain lane, we can get a variation of 10%. That was not sufficient. It's not sufficient to slow down the hydrogen enough and avoid the diffusion flame. So we are investigating different possibilities for that. And moment we are exploring this on the left, where we inject fuel and air premixed already in the cavity. And that's the image from, the PhD that is working on it, which is Vittorio De Lauso. As you see, you have a flame, a certain flame in the cavity. Unfortunately, because of the strong diffusion of hydrogen, since we burn rich, the leftover hydrogen run quickly towards this region of the inlet here where there is air and give a diffusion flame. Now, this is a problem we're trying to solve. We haven't yet, but that's what we're working on. In general, though, since strain is not enough, we're trying to slow down the reactions by injecting low temperature. This quite is interesting, and there is laminar flames that have been investigated recently experimentally. We see that hydrogen, if it is premixed, even at 100 Kelvin, you still have a flame in laminar conditions, at least. So you can actually go very down with the temperature and try, at least that is the idea that we had, try to slow down the flame. So avoid the diffusion. And if you inject at 150 Kelvin, you have two effects. First, the flame changes position inside the cavity, but also you see that the effect in turn on the diffusion flame, it's better in the sense that the flame is not as strong as before. You are allowing a bit more mixing. In general, though, there is an effect that we didn't consider before, and the PhD actually found it, Vittore Dell'Auso, that basically as you go down, the decrease, well, the slowing down that you was expecting from the laminar condition doesn't happen at turbulent condition, because you get a large scale wrinkling, as you see in this graph. And because the heat release ratio is stronger at low temperature, you have to think that as you increase the temperature, the CP, the heat capacity increases. So actually the jump that you have is lower and lower. So that means that this jump of temperature is higher at a low temperature injection. And so we are slowing down overall, but not as much as we thought. And that's what we're working on at the moment to try to optimize this at a low temperature injection. So that is it. I hope I was more or less in time. I think so. And that's what we're working on at least for the part of strain. There is, of course, many other projects that I briefly touched base, where we are tackling hydrogen from other point of views. So today I showed the part of strain and how that could be used to reduce NOx and maintain, at the same time, have a stable flame. We're still working on, and of course, if you are interested or you would like or have ideas in this direction, will be very welcome to contact me or the PhD students working on it at any time.
Thank you, Ivan. Thank you very much. Very, very nice talk. There is time. Indeed, you are right on time. So there is time for questions. I look at the audience. If there are questions, raise hands. You can also write it in the chat, and I will read it. So there is, I see already there is a raised hand. Sandra?
Hello, can you hear me?
Yes.
Okay, thanks for your very interesting presentation. I think it was really interesting, especially to see the part in which you used the strain of the flame to suppress thermodiffusive instabilities and acoustic instabilities as well. And I wanted especially to ask, because for what I understood, you used a premixed flame at low equivalence ratio, maybe because you have higher thermodiffusive instability and also lower on NOx. And I wanted to ask if you have also looked at the impact on if there is a variation of this critical strain rate, if you use different equivalence ratio or pressure or different flame regimes. Thanks for your answer.
Yeah, thanks. Very interesting question. I went perhaps a bit fast, but we have examined different equivalence ratios. We have stayed so far in the lean regime, but we have examined different equivalence ratio, which are either very lean to be sure that the mass chain length starts negative, or on the other side of the mass chain length, so when it is almost zero, slightly positive. The behavior that now for the thermodiffusion instabilities, we have focused on the linear part to make sure that we had the thermodiffusion instabilities. And for the thermoacoustic analysis, it's true. At the moment, we only have done the very lean condition. But the reason is because basically, if you go to higher equivalence ratio, this point that you see here moves towards the right. It's true that we was a bit lucky that we got this, because if we were at 0.7, in the range that we were investigating, perhaps we couldn't have seen this inversion. But this is very lean. We have this inversion that makes things quite interesting. But I mean, so in general, the effects that I'm talking about are generalizable to the entire lean regime. It's not just at one equivalence ratio.
Okay, thank you.
Thank you. I'm looking if there are other questions. I see another end. Where is it? Is it always? Oh, it's still Sandra. I think there is one from Salvatore, right?
Yes. Thank you, Ivan, for this interesting talk. I was wondering if you are going to investigate also swirling flame and the effect of swirl and on the stretch and all these analyses that you have shown us, and if you plan to also look into the hydrodynamic instability that a swirling flame can create.
Yes. So the idea is I didn't mention, as I went briefly and say, okay, we are investigating as possible configuration of the lean premixed. Now, within that, we're trying to figure out how to add strain on the flame. One way is to use to go to swirl flames, of course, and it's in the schedule. Now, exactly how though is not as straightforward, because if you introduce strain, is true with the shear, but you introduce also vorticity. You need to have a mean applied strain for things to work in the direction of the suppression of NOx. So we're thinking counterflow. Sorry, not counterflow, but counter-rotating as well flows. We're thinking. We haven't yet arrived to that phase where we examine real geometries where we have the swirl. But it may also happen that it's not easy with the swirl, and we will go to another system. But it's one of those that are that we have to analyze. If you have ideas as well, you can always discuss.
No, I was sure. No, I was relying on you, on your exploratory desire to to investigate these conditions, which are very, very important. I mean, it's what's being used also a lot in for gas turbines. Okay, thanks a lot.
Thank you.
Yeah, in the chat.
Yeah, there's a question on the chat. So there is so there is a question about are there any ongoing efforts, to look at the effect of preferential diffusion on hydrogen with external excitation of the flow in the premixed regime? And he adds whether the response of the flame exceeds the usual 10% excitation amplitude towards a flame describing function.
Well, not sure if you mean something different from this. I mean, these simulations that you see here, where we were forcing the inlet to get the FFT in the linear regime. Not sure if you mean trying also the nonlinear regime. I'm not sure if I grasped the question.
If you
just said
mute
turbulent
yourself,
regime.
easier maybe. In turbulence.
It said turbulence. Yeah.
In turbulent conditions, yes, of course. This was a first step to try to see if there is any kind of effect of strain only, because turbulence then will make everything more uncertain. But yes, those are in due phase. Remember, the PhD EMRE, which is working on it, has started very recently, like 6 months ago. So there is a lot of time for, well, it's never enough time, but there is time where we are going to investigate all these other parts.
And Ivan, maybe I have a question. So when you talk about the residence time and the fact that it's not the main, or it's not relevant in your case, is of course, I mean, is this regardless of the main contribution pathway? What I mean is that, of course, I suppose that if your main pathway for NOx formation is the thermal one, then you should see an effect, right? If it's NNH, maybe it's a different story.
So what I meant, okay, there are two things. First of all, as you increase the strain, the NOx reduction happens along all the pathways. So
Yes.
NTO, thermal, and NNH.
Yeah, you showed it. Yes.
That is it's not shown here separately, but it's shown in the paper.
Yeah.
But it's stronger with the thermal one because we examined in the paper at equivalence ratio 0.7 where thermal was dominant. So you could see that the reduction is stronger because of the thermal route, but not because you're decreasing the temperature, which is actually increasing because of the subaradiabatic effect. It's because of the displacement of the H radicals, as I was saying. Now, what I was saying in this graph here is that you could think because of the configuration, to increase the strain, you increase the speed of the reactants.
Yeah, okay.
And then you can think, okay, you have less NOx because it requires time to form and you don't see that. You don't give enough time, so you think that is less. But that's why I say, no, we are compared at different flame. So for same time of reactions. And
okay, I understand.
we clearly see that. We also check the flux. So, and now we are repeating everything at with the DNS at turbulent condition, we see the same. So at least in the limit of the best high fidelity we could do from
no, it's clear.
Medical point of view, that happens. Now, of course, if you can add an experiment, it would be nice. A moment we haven't, unfortunately. I think I discussed with you about this at a certain point.
Thank you. It's very, very interesting. Let's see if there is another question. I don't see any other question. In that case, thank you again, Ivan, really for the very nice talk. Thank you everyone for having attended, and see you for another lecture.
Thank you again for inviting. And
Bye-bye, everyone. Have a nice weekend.